Welcome back. So, just as a reminder, we're still talking about the Turing instability, and I definitely am pushing this, and I'm not even going to be through after this time. And at this point, we've reached the part of the story that's, of course, voluntary for those of you listening. Um, I'm not going to give a homework necessarily about what I'm doing now, and nor am I really expecting you to dig down into every one of the details. But I think it's important to see the tools that are brought to bear on a problem like this. And so I would like to think of it as enrichment, and the way that I might view this is, you go to New Zealand and maybe you're going to go hang out in the fjords and do some hikes and stuff, but on the way there, you stop at a sheep farm and you watch border collies. It's just kind of an enrichment. So I feel that, seeing the way that, for example, Cross and Hohenberg, two famous physicists that wrote this beautiful long article in Reviews of Modern Physics in the 1980s, and then subsequently Mike Cross wrote a book with Greenside. It's really quite beautiful the way that they use PDEs to describe the Turing instability. And so I'm going to try and give a flavor of that in this vignette. But as I point out, it's pretty technical, and there's a lot of algebra. There's a lot of possibilities for me to go off the rails in terms of my algebra. And then there's some subtle arguments that have to do with signs of traces and determinants of matrices, which you'll see as I get there. So at any rate, what are we up to? We're up to comparing and contrasting the two predominant methodologies for thinking, or frameworks for thinking about spatial patterning. One of them is the Wolpert kind of view, which is based on positional information, and then the other is the general category of Turing instabilities. And I'm looking forward in the next vignette to telling you about a beautiful article from James Sharp, who's at EMBL in Barcelona, in which he tries to turn down the temperature on the supposed dichotomy between those two worldviews. And I really like that, because I feel again and again in science we have these kinds of controversies. If you go back to the late 1800s, there was this controversy between Pasteur in France and the Buchners about what is an enzyme. And Pasteur had this notion that enzymes were part of the yeast life cycle, and they were critical to how it actually converts sugars into energy and stuff. And then the Buchners had this mindset that, come on, this is just another molecule, just doing chemistry. And it was very hostile in a way. And yet, in retrospect, 120 years later, you just look at it and you're like, come on, they're both right. And in some sense, this notion that, it's all Turing or all positional information, it just seems like a bit of wasted energy. And I already mentioned this in the context of allostery, where I told you about the MWC model. I did not really talk about the KNF model, but that's another example of a situation where the temperature or the heat can be turned down and without any problem. So at any rate, I'm excited to talk about that. Why did I bring up James Sharp? Because not only does he make that point, but we're going to use his work as a way to think about the fact that Turing is more general than this activator-inhibitor architecture that I have been focusing on, basically drawn straight out of Turing's paper. Okay, so with that as background, what are we going to do here? So what we're going to do, you can see there's a big mess here. We are going to, it's a lot of calculations. So we're going to do a continuous version of Turing. And I don't know if I've explicitly mentioned this already in the course, but I think a very, very important overarching thought to carry around with respect to the mathematical modeling of the natural world is a fluency in passing back and forth between continuous and discrete representations of whatever it is that we're thinking about. So previously, I wrote down a bunch of coupled ordinary differential equations where there was a differential equation basically describing the XR and the YR in the rth cell, but they were coupled to each other. What I'm going to do now is I'm going to use the reaction diffusion sort of mentality, and I'm going to cut straight to it. I'm going to write down dx by dt is equal to dx, and then Laplacian of x, and then plus, maybe I don't need the subscript, plus f of x and y, and dy by dt is equal to dy, and then grad squared y plus g of x and y. So at first cut, maybe this looks very different from what we wrote before, or maybe it looks very much the same. What I've done is I've basically, here, I have replaced, before what we had was we had y of r plus 1 plus y of r minus 1 minus 2 yr, and this is the discrete version of d squared y by dx squared. So in fact, this is discrete, and this is continuous, and all I'm really advocating here is that we gain something by converting from the ordinary differential equation language to the partial differential equation language. These are now partial differential equations. What does that mean? It means that x and y are functions of little x and t, and that's true for both of them. And so I have derivatives involving both x and t. So fundamentally, the differential equation that I've written down is partial differential equation because it involves partial derivatives. So what do we do now? So what we're going to do is we're going to advance trial solutions just like we did in the past. And the trial solutions are going to be of the form x of t. So first let's linearize. Sorry about that. So first thing I'm going to do, first step, is linearize. So we're once again engaged in asking the question, is this are the fixed points stable? And I'm going to once again say that h comma k is the fixed point, and the implication of that statement is that f of h and k is equal to g of h and k, which is equal to 0. What that means is that the chemistry is not firing. If I sit there at that concentration, then the system will be entirely homogeneous, and there will be no chemical reactions that take place. So I'm going to replace the x equation by this equation where what happens is that I get an a11 times x plus an a12 times little y, where a11 is equal to df by d big X, and a12 is df by d big Y, just like we did before. In other words, what I'm doing is these bits correspond to doing f of x comma y is approximately equal to let's be a little bit more careful here. What I'm doing is I'm saying f of h plus x and k plus little y is approximately equal to f of h comma k, and then plus df by d big X times x plus df by dy times little y. That's what I mean by my linearization. So that's what I've done. And so similarly, I have dy by dt is equal to dy d squared y plus a21x plus a22 little y. So these are our equations, our linearized partial differential equations that describe our activator-inhibitor system in space. So these are they're linearized. You can see, you look at them and you see that they're linear. It's a linear partial differential equations. And now what we need to do is we need to have a go at trying to see whether or not the solutions are stable. So step 2 is that we consider the trial solution x of t is equal to x naught of t, and then e to the I q x, and then y of t is equal to y0 of t e to the I q x. So what is this? This is, once again, it's a periodic solution. Note that the units of q has units of 1 over length, and to be more pedantic about it, q is defined as 2 pi over the wavelength of the perturbation that we're thinking about. So we're considering a perturbation of wavelength lambda, and what we want to find out is, does that perturbation grow or shrink in time? So that's the activity that we're going to undertake now. So if I plug these trial solutions into our PDEs, so plug into the PDEs, what will happen? Well, what I want you to notice is that if I do, this is by the way, this was probably notationally not, it was a little notationally sloppy. I should have said here little x of x and t. This becomes very, in a way, crummy as notation, and I shouldn't have done it, but it's too late to turn back now. So I've got x doing double duty, right? Bad. So it's doing double duty in the sense that lowercase x in these places like these derivatives, this thing, that is the concentration. And then this x right here, this one, that's the position. So terrible. And I'm hoping that you'll forgive me, first of all, but I'm hoping that you'll force yourself to, have the discipline to make sure you see the context. And what do I want to say? I mean, how bizarre is it that there's this word in the English language called READ, and depending on how I choose to pronounce it, it's either present or past tense of reading. I read or I read. Just as an aside, I always thought it was kind of cool seeing my kids. I remember very well saying, I readed the book. And at first that's so harsh on your ears, you're taken aback by it. But then if you actually permit yourself to stop and think about where the kid is coming from, then you have to marvel at the powers of generalization that saw that there's a rule, that there's a pattern, which is that we add ed to regular verbs to make them past tense, and somehow, they try out that rule with no one ever telling them that they should try that rule. It just happens naturally. Anyway, why do I go off on that point? Because context does matter, and so unfortunately, I'm stuck with this double usage of x. Okay, so we plug this into the PDEs, and what I want you to see is that the second derivative, thus, and I'm going to use the y one, d squared y by dx squared is minus q squared, and then y0 of t e to the iqx. Why do I say that? Because every derivative I take with respect to x brings down an iq, and so if I have two iq's, then I get I times q times I times q, I squared is minus 1, and there you go. So you get this thing. So without further ado, I'm going to straight away write this in matrix language. So this is what we're left with as the problem that we need to solve. We're left with a11 minus dx q squared, and then a12, a21, and a22 minus dx q squared, and that's acting on xt, x0 of t, y0 of t. Okay, so I'm claiming that this is equivalent to our original PDE now. In other words, because we made this trial solution, what happened is that, if you look back up here, I took my second derivative, and that turned this guy into a minus q squared dx times x. I already have an a11x, So together, these two are going to make the a11 minus dxq squared times x0, and then this is going to just be sitting there the way that I did it. So that's the matrix. And you'll recall, I'm not going to plug it in, but we seek solutions of the form e to the sigma t, and then we ask ourselves whether sigma is greater than 0 or less than 0. Where that leads us is it demands of us finding the eigenvalues of this matrix, which I'm going to call A. So, I don't know. Let me call it little a, perhaps. I don't know what I'm calling it. So I'm going to call it little a. So I need the eigenvalues of that matrix. So what is that? Let's review what that means. So if I want the eigenvalues of a 2 by 2 matrix, let's just write it out explicitly. So I have the matrix A11, and then minus sigma A12, A21, and A22 minus sigma. That's the matrix that I want. And I need determinant of that thing to be equal to 0. So what does that correspond to? Let's multiply it out. Well, so the determinant is A11 minus sigma, A22 minus sigma, and then minus A12, A21 equals 0. This gives me A11, A22 minus A12, A21. I'm writing that way for a reason. And then I have minus A11 plus A22 times sigma. And then I have plus sigma squared equals 0. This thing is the determinant of A. And this thing is called the trace of A. So just recall from your previous experience with matrices that the determinant is, at least for the 2 by 2 case, is very straightforward. You take the left to right diagonal, multiply those two things together, and then you subtract the one going in the other direction. That's clearly what I have right here. The trace is just take the sum of the diagonal elements. That's what it means. So it's a name. I'm giving a name to a thing. It's a name that lots of people know and use in the sort of applied math, linear algebra world. But if you haven't heard it before, it doesn't matter. It's just a name. So I'm giving you the name. I'm in a city. It's got a name called San Francisco. It's just a name. So anyway, we've got these two things, and now I can actually solve this equation, and let's do that. So I find that sigma is equal to minus b over 2a, you'll remember. So that's a1, sorry, I'm gonna be cleaner about it. That's equal to trace of a, and then plus or minus, oh, and there's a 1/2, and then plus or minus, and then 1/2. And then I have b squared, which is trace a squared, minus 4, and then a, which is the coefficient of sigma squared, and then c, which is determinant of a. Great. So those are eigenvalues. That's it. And from here, everything else becomes an exercise in our imaginations and our understanding. So I'm going to see if we can try to reason out what this thing wants to tell us. So this is cool. So observation number 1 is that, let's see. So we know that for stability, that we need both eigenvalues to be negative. So let's think first about case 1, which is stable in the absence of diffusion. So what does that imply? Well, that definitely means that trace of A has got to be less than 0. And if diffusion is 0, our trace is nothing more than A11 plus A22. So this says that A11 plus A22 is less than 0, and thus what I can say is at least one of A11 and A22 is negative. I can say that. Now let's think about case 2, stable without diffusion, and then unstable with diffusion. That's kind of like the cases that we did earlier. You'll remember that, like when I looked at the 2-cell case, we had a linear stability analysis, and if you reflect on it, what you will find, if you go back and review what I did, if you had set diffusion equal to 0, then those cases would have been stable, which means the homogeneous state would have just sat there as the homogeneous state, and if you perturb the homogeneous state, it would return to the homogeneous state. So we want to think about this case, and what I learned from that is that if you look at this expression, all the action really is right here. Why do I say that? Because I already know that the eigenvalue of interest is this +1. I'm trying to find out, are both eigenvalues negative? Well, if trace A is negative and then I subtract something from it, that's even more negative. But if I add something, I'm in peril of having a net positive eigenvalue. And so I guess what I would say is that, what do I want to say about this? So we're interested in the case where this thing is unstable, and that means that when I take this plus root, I need to add something that's bigger than this term. In order to achieve that, I better make sure that this sign right here is positive. So that means I also have this second condition, which is that determinant of A is greater than 0. Wait, did I say that right? I want that sign to, sorry, I said it backwards. I want that sign to be net positive, which means the determinant of A needs to be less than 0. So we have this requirement that determinant of A is less than 0. Now, hold on a sec. I need to review my musings from earlier. Yeah. Okay. Right. Okay. So I want to let's calculate the determinant. So compute the determinant of our matrix A. You'll recall that means that we've got, let me bring down the matrix. So the determinant of this thing, so determinant of this is equal to A11 minus dx q² times A22 minus that's dy q². Sorry, please go fix that if you are taking notes. Minus A12, A21 equals 0. No, I didn't say yet. So that's the determinant. We can expand this out, and what we get is A11, A22 minus A12, A21, and then we have minus dx q² A22 minus dy q² A11, and then plus dx dy q to the 4th. This is a quadratic function in q². Further, dx times dy is greater than 0, So this thing is concave upward, right? In other words, if I plot it, because the largest term, q fourth, and I'm plotting it in the variable q squared, this will be concave upward. So I want to find where the minimum is. So find the minimum. Find the q that renders this value the least value it can have. So find minimum. So that means d by dq squared of this determinant. I'm just going to look upstairs, and what I'm going to get is I'm going to get 2 dx dy q squared, and then minus dx a22 minus dy a11. And I set that equal to 0 in order to find the minimizer. So what this tells me is that q min squared is going to be equal to dx a22 plus dy a11 divided by 2 dx dy. Okay, I need to stop, take a pause, and keep our eye on the prize. So what are we doing? Why are we going through all these technicalities? Well, first of all, it's a meditation in a way. There's a calculation here, and this is a very standard linear stability analysis, and it's got some relationship to the one we did earlier for the mutual repression switch. It's a little bit messy, but really what it requires, at least I'm speaking for myself, what it requires is just keeping focused and continually reminding myself of what we're trying to do. So what are we trying to do? We're looking for the case where without diffusion, the thing is stable, and with diffusion, it becomes unstable. In order for that to happen, I need the determinant to be less than 0. I've now found a q min. I found the q vector, or the wave number, which leads to the lowest value of the determinant as a function of q. So that's going to be a special wavelength, I guess is the way I want you to think of it. So now we're going to plug this back into determinant of A. To find determinant of A at the minimum, or at the minimizer value of Q. So that's what we need to do. So I need to take this Q min squared, and I need to put it back in this expression up here for the determinant. Yikes. I've done this, but I don't even remember doing it. So I think I better go look. So this thing is, this is the determinant of A, and now the proposal is we plug in the value for Q squared. So this gives me A11, A22, minus A12, A21, and then minus dx A22 plus dy A11, and then times so the same thing. That's useful. I'm going to just square it, divided by 2 dx dy, and then plus, oh boy, I think I lost my, we're good, okay. Plus, now I got to do the dx dy, so dx dy, and then I need to square Q squared, so that gives me dx A22 plus dy A11 squared over 4 dx dy. These are both squared. And this leaves me with A11, A22 minus A12, A21. Woo! And then minus 1/4, and then dx A22 plus dy A11 squared over dx dy. So that's the determinant of A. Now, what do we know? What do we know? We've already said that this, oh, no. Okay, I think I need to look at my notes, so bear with me. So did I do this right? Yes. All right, yeah, I'm going to copy this thing that I wrote earlier. Sorry. All right, so let's paste this in and stare at what I wrote to myself earlier. So I know that I want the determinant to be negative. So this thing is less than 0, and that implies this line. Oh, man. Shoot. So that implies this line. And what I say on the left is that I know this already is greater than 0 because of stability without diffusion. So what do I mean by that? If you go back to the diffusion case, the no diffusion case, where was that? Oh, here, this thing. So if you go back to this, and in the absence of diffusion, I need for this to be negative for both eigenvalues. That means I need this guy to be less than this one, which means I need this to be negative, which means I need determinant to be positive in that case. Okay? So that's the reason I'm saying, because of stability without diffusion, I already know that that part's positive. And so now I can see that that implies that this thing has got to be greater than 0. And we already showed that one of the A11, A22s is negative. So now I've got to make sure that, that the other A11 or A22 is greater than 0. So I've demonstrated that one of them is greater than 0 and one of them is less than 0. So the conclusion is one of A11, A22 is greater than 0, other is less than 0. And I can actually say a priori, A11 is the one that's greater than 0. Why is that? Because if you look back at my equations that we wrote down, here's the intuition. If you look at the equations right here, then if A11 is greater than 0, then that means that X reinforces. It's actually leading to its own production with a plus sign. If A22 is negative, then that means that it's the inhibitor. It's inhibiting itself. It's basically reducing the amount of itself that's produced. So that's the intuition that I'm attaching to A11 and A22. And I think I need to add another page. Where am I? Okay, yeah. Add page. Okay, A11 is greater than 0. A22 is less than 0. And we're almost through with the mathematical analysis here. We can figure out what the actual wavelength then is. And the reason I claim that is that, let's see, I can show you what I wrote down. earlier. Oh, that's a mess. Yeah, I guess the last thing I want to comment on is that I can define two length scales, which I'm showing you right here. Okay, if you think about it, we know that diffusion coefficient has units of length squared divided by time, and we know that A11 has units of 1 over time. If you go back and look at what I did earlier, you'll see that it has units of 1 over time, and so so what that tells us is that lambda x is equal to square root of dx over A11, and lambda y is equal to square root of dy over minus A22. So I have these two lengths. I can substitute these into this equation up here, and what I get out is basically a relationship. So I figured out Q min squared in terms of these two lengths. Okay, so I think I'm gonna stop here, and what I promise in the next vignette, what I'm gonna do is I'm gonna step back now from the mathematics. I'm gonna try and talk about what it all means. This was primarily a technical excursion to show how to do the linear stability analysis.